Okay, in this video we are going to learn the wave nature of light. Light travels through space as a wave and similar to an ocean wave. Wavelength is a distance of the light where light wave travels in one cycle. And frequency is the number of the wave cycles completed in each second. Light usually travels at a constant speed and it's 3 times 10 raised to 8 meter per second. Wavelength versus frequency. So we'll see how the wavelength, if the long the wavelength and the frequency is shorter. And if it is the shorter the wavelength of the light, the higher the frequency. So there is an indirect relationship between wavelength of the light and frequency. If wavelength increase, let's go back. If wavelength increase, frequency decrease. If wavelength decrease, frequency decrease. If frequency increase, you can see here high energy blue light, high frequency, shorter wavelength, low energy red light, long wavelength, short frequency. So light usually refers to radiant energy that is visible to the human eye. Visible light spectrum is a range of wavelengths between 400 to 700 nanometer. Radiant energy has a wavelength lower than 400 nanometer and greater than 700 nanometer, and we cannot see through human eyes. And you can see here these are visible light spectrum from blue to red, from 400 nanometer to 700 nanometer wavelengths. So radiant energy spectrum. It is a complete radiant energy spectrum. It's an uninterrupted band or continuous spectrum. Radiant energy spectrum includes many types of radiation, most of which is invisible to human eye. For example, cosmic ray, gamma ray, X-ray, ultraviolet ray. Of course, visible we can see through our eyes. And then infrared, microwave, TV, radio. Those are in radiant energy spectrum. And let's talk about quantum concept. Quantum concept states that energy is present in small and discrete bundles. For example, a tennis ball that rolls down a ramp loses potential energy continuously, and a tennis ball, when it rolls down the staircase, loses potential energy in a bundle, and that loss is quantized. And Neil Bohr speculated that electrons orbit the nucleus in a fixed energy level. Electrons are found only in a specific energy levels, nowhere else. Electron energy levels are quantized. Now we'll talk about emission line spectrum. When an electrical voltage is passed across a gas in a sealed tube, a variety of narrow lines is seen. You can see these lines are emission line spectrum. For example, this is a hydrogen gas in this filament, and when we pass voltage where hydrogen atoms excited, and you can see violet, blue, green and red color in emission spectrum. So Bohr realized that this was the evidence he needed to prove his theory. Electrical charge temporarily excites an electron to higher orbit, and then the electron drops back to its normal level, then photon gives up. Red line is the least energetic and corresponds to an electron dropping from level 3 to level 2. You can see, and that's where they can see the lights. The emission spectrum of each element is unique. It's like fingerprints. We can use the line spectrum to identify elements using their atomic fingerprint. Here you can see helium has different, lithium has different, sodium, mercury, all elements has different. Now in next one we'll talk about energy levels and sublevels.